straight line fit will eventually become negative. Let's bend the curve here, so it just ends up 0 here. So this thick blue line ends up being, your function for predicting the price of a house as a function of large neural networks. So what exactly is a neural network? In this video, let's try to give you some of the basic intuitions. Let's start with a housing price prediction example. Let's say you have a data set with 6 houses, so you know the size of the houses in square feet or square meters, and you know the price of the house, and you want to fit a function to predict the price of a house as a function of its size. So if you're familiar with linear regression, you might say, well, let's fit a straight line to this data. So, maybe you get a straight line like that. But to be a bit fancier, you might say, well, we know that prices can never be negative, right? So instead of a straight line fit, which will eventually become negative, let's bend the curve here. So it just ends up 0 here. So this thick blue line ends up being, your function for predicting the price of a house as a function of its size, whereas 0 here, and then there's a straight line fit to the right. So you can think of this function that you've just fit to housing prices as a very simple neural network. It's almost the simplest possible neural network. Let me draw it here. We have as the input to the neural network the size of a house, which we want to call x. It goes into this node, this little circle, and then it outputs the price we're going to call y. So this little circle, which is a single neuron in a neural network, implements this function that we drew on the left. And all that the neuron does is it inputs the size, computes this linear function, takes a max of 0, and then outputs the estimated price. And by the way, in the neural network literature, you see this function a lot. This function which goes at 0 at some time and then takes off as a straight line. This function is called a ReLU function, which stands for rectified linear unit. So ReLU. And rectified just means taking a max of 0, which is why you get a function shape like this. You don't need to worry about ReLU units for now, but it's just something you see again later in this course. So if this is a single neuron neural network, really a tiny little neural network, a larger neural network is then formed by taking many of these single neurons and stacking them together. So if you think of this neuron as being, like a single Lego brick, you then get a bigger neural network by stacking together many of these Lego bricks. Let's see an example. Let's say that instead of predicting the price of a house just from its size, you now have other features. You know other things about the house, such as the number of bedrooms, which we want to write as pound bedrooms. And you might think that, one of the things that really affects the price of a house is family size, right? So, can this house fit your family of 3 or family of 4 or family of 5? And it's really based on the size in square feet or square meters and the number of bedrooms that determines whether or not a house can fit your family's family size. And then maybe the zip code in different countries is called the postal code, right, of the house. The zip code maybe is a feature that tells you, walkability. So is this neighborhood highly walkable? Can you just walk to the grocery store and walk to school, or do you need to drive? So some people prefer highly walkable neighborhoods. And then the zip code, as well as, the wealth maybe, tells you, right, certainly in the United States, but some other countries as well, tells you how good is the school quality. So each of these little circles I'm drawing can be one of those ReLU, rectified linear units, or some other slightly nonlinear function, so that based on the size and number of bedrooms, you can estimate the family size. Based on zip code, estimate walkability. Based on zip code and wealth, you can estimate the school quality. And then finally, you might think that, well, the way people decide how much they're willing to pay for a house is they look at the things that really matter to them, in this case, family size, walkability, and school quality, and that helps you predict the price. So in this example, X is all of these 4 inputs, and Y is the price you're trying to predict. And so by stacking together a few of the single neurons, or the simple predictors we had from the previous slide, we now have a slightly larger neural network. Part of the magic of a neural network is that when you implement it, you need to give it just the input X and the output Y for a number of examples in your training set, and then all these things in the middle, it will figure out by itself. So what you actually implement is this, where here you have a neural network with 4 inputs. So the input features might be the size, number of bedrooms, the zip code or postal code, and the wealth of the neighborhood. And so given these input features, the job of the neural network will be to predict the price Y. And notice also that each of these circles, these are called hidden units in the neural network, that each of them takes as input all 4 input features. So for example, rather than saying this first node represents family size, and family size depends only on the features x1 and x2, right? Instead, we're going to say, well, neural network, you decide whatever you want this node to be, and we'll give you all 4 input features to compute whatever you want. So we say that the layers, that is this input layer and this layer in the middle of the neural network, are densely connected because every input feature is connected to every one of these circles in the middle. And the remarkable thing about neural networks is that given enough data about X and Y, given enough training examples with both X and Y, neural networks are remarkably good at figuring out functions that accurately map from X to Y. So that's a basic neural network. It turns out that as you build out your own neural networks, you probably find them to be most useful, most powerful in supervised learning settings, meaning that you're trying to take an input X and map it to some output Y, like we just saw in the housing price prediction example. In the next video, let's go over some more examples of supervised learning and some examples of where you might find neural networks to be incredibly helpful for your application. As well. There's been a lot of hype about neural networks, and perhaps some of that hype is justified given how well they're working. But it turns out that so far, almost all the economic value created by neural networks has been through one type of machine learning called supervised learning. Let's see what that means, and let's go over some examples. In supervised learning, you have some input X, and you want to learn a function mapping it to some output Y. So for example, just now we saw the housing price prediction application where you input some features of a home and try to output or estimate the price Y. Here are some other examples that neural networks have been applied to very effectively. Possibly the single most lucrative application of deep learning today is online advertising. Maybe not the most inspiring, but certainly very lucrative, in which by inputting an ad, information about an ad that a website is thinking of showing you, and some information about the user, neural networks have gotten very good at predicting whether or not you click on an ad. And by showing you and showing users the ads that you're most likely to click on, this has been an incredibly lucrative application of neural networks at multiple companies. Because the ability to show you ads that you're more likely to click on has a direct impact on the bottom line of some of the very large online advertising companies. Computer vision has also made huge strides in the last several years, mostly due to deep learning. So you might input an image and want to output an index, say from 1 to 1,000, trying to tell you if this picture might be any one of, say, 1,000 different images. So you might use that for photo tagging. I think the recent progress in speech recognition has also been very exciting, where you can now input an audio clip to a neural network and have it output a text transcript. Machine translation has also made huge strides thanks to deep learning, where now you can have a neural network input an English sentence and directly output, say, a Chinese sentence. And in autonomous driving, you might input an image, say a picture of what's in front of your car, as well as some information from a radar. And based on that, maybe a neural network can be trained to tell you the position of the other cars on the road. So this becomes a key component in autonomous driving systems. So a lot of the value creation through neural networks has been through cleverly selecting what should be X and what should be Y for your particular problem, and then fitting this supervised learning component into often a bigger system, such as an autonomous vehicle. It turns out that slightly different types of neural networks are useful for different applications. For example, in the real estate application that we saw in the previous video, we use a relatively standard neural network architecture, right? Maybe for real estate and online advertising, it might be a relatively standard neural network, like the one that we saw. For image applications, we'll often use convolutional neural networks, often abbreviated CNN. And for sequence data, so for example, audio has a temporal component, right? Audio is played out over time, so audio is most naturally represented as a one-dimensional time series. It's a one-dimensional temporal sequence. And so for sequence data, you often use an RNN, a recurrent neural network. Language, English and Chinese, the alphabets or the words come one at a time. So language is also most naturally represented as sequence data. And so more complex versions of RNNs are often used for these applications. And then for more complex applications like autonomous driving, where you have an image that might suggest more of a CNN, convolutional neural net structure, and radar info, which is, something quite different, you might end up with a more custom or some more complex hybrid neural network architecture. So just to be a bit more concrete about what are the standard CNN and RNN architectures. So in the literature, you might have seen pictures like this. So that's a standard neural net. You might have seen pictures like this. Well, this is an example of a convolutional neural network. And we'll see in a later course exactly what this picture means and how you can implement this. But convolutional networks are often used for image data. And you might also have seen pictures like this. And you learn how to implement this in a later course. Recurrent neural networks are very good for this type of one-dimensional sequence data that has maybe a temporal component. You might also have heard about applications of machine learning to both structured data and unstructured data. Here's what the terms mean. Structured data means basically, databases of data. So for example, in housing price prediction, you might have a database with a column that tells you the size and the number of bedrooms. So this is structured data. Or, in predicting whether or not a user will click on an ad, you might have information about the user, such as the age, some information on the ad, and then labels Y that you're trying to predict. So that's structured data, meaning that each of the features, such as size of a house or number of bedrooms or the age of a user, has a very well-defined meaning. In contrast, unstructured data refers to things like audio, raw audio, or images where you might want to recognize what's in the image, or text. Here, the features might be the pixel values in an image or the individual words in a piece of text. Historically, it's been much harder for computers to make sense of unstructured data compared to structured data. And in fact, the human race has evolved to be very good at understanding audio cues as well as images. And then text was a more recent invention, but people are just really good at interpreting unstructured data. And so one of the most exciting things about the rise of neural networks is that thanks to deep learning, thanks to the features such, deeper neural networks are, very good for this type of one-dimensional, sequence data that has maybe a temporal component. You might also have heard about applications of machine learning to both structured data and unstructured data. Here's what the terms mean. Structured data means basically, databases of data. So for example, in housing price prediction, you might have a database with a column that tells you the size and the number of bedrooms. So this is structured data. Or, in predicting whether or not a user will click on an ad, you might have information about the user, such as the age, some information on the ad, and then labels Y that you're trying to predict. So that's structured data, meaning that each of the features, such as size of a house or number of bedrooms or the age of a user, has a very well-defined meaning. In contrast, unstructured data refers to things like audio, raw audio, or images where you might want to recognize what's in the image, or text. Here, the features might be the pixel values in an image or the individual words in a piece of text. Historically, it's been much harder for computers to make sense of unstructured data compared to structured data. And in fact, the human race has evolved to be very good at understanding audio cues as well as images. And then text was a more recent invention, but people are just really good at interpreting unstructured data. And so one of the most exciting things about the rise of neural networks is that thanks to deep learning, thanks to neural networks, computers are now much better at interpreting unstructured data as well compared to just a few years ago. And this creates opportunities for many new exciting applications that use speech recognition, image recognition, natural language processing on text, much more than was possible even just 2 or 3 years ago. I think because people have a natural empathy to understanding unstructured data, you might hear about neural network successes on unstructured data more in the media, because it's just cool when a neural network recognizes a cat, and we all like that and we all know what that means. But it turns out that a lot of the short-term economic value that neural networks are creating has also been on structured data, such as much better advertising systems, much better product recommendations, and just a much better ability to process the giant databases that many companies have to make accurate predictions from them. So in this course, a lot of the techniques we'll go over will apply to both structured data and to unstructured data. For the purposes of explaining the algorithms, we will draw a little bit more on examples that use unstructured data. But as you think through applications of neural networks within your own team, I hope you find both uses for them in both structured and unstructured data. So neural networks have transformed supervised learning and are creating tremendous economic value. It turns out, though, that the basic technical ideas behind neural networks have mostly been around, sometimes for many decades. So why is it then that they're only just now taking off and working so well? In the next video, we'll talk about why it's only quite recently that neural networks have become this incredibly powerful tool that you can use. If the basic technical ideas behind deep learning, behind neural networks, have been around for decades, why are they only just now taking off? In this video, let's go over some of the main drivers behind the rise of deep learning, because I think this will help you better spot the best opportunities within your own organization to apply these to. Over the last few years, a lot of people have asked me, Andrew, why is deep learning suddenly working so well? And when I'm asked that question, this is usually the picture I draw for them. Let's say we plot a figure where on the horizontal axis we plot the amount of data we have for a task. And let's say on the vertical axis we plot the performance of our learning algorithm, such as the accuracy of our spam classifier or our ad click predictor, or the accuracy of our neural net for figuring out the position of other cars for our self-driving car. It turns out if you plot the performance of a traditional learning algorithm like support vector machine or logistic regression as a function of the amount of data you have, you might get a curve that looks like this, where the performance improves for a while as you add more data, but after a while the performance pretty much plateaus. Right? This is supposed to be a horizontal line, didn't draw that very well. It was as if they didn't know what to do with huge amounts of data. And what happened in our society over the last 20 years maybe is that for a lot of problems, we've went from having a relatively small amount of data to having, often a fairly large amount of data. Right? A lot of this was thanks to the digitization of a society where so much human activity is now in the digital realm. Our society over the last 20 years maybe is that for a lot of problems, we've went from having a relatively small amount of data to having, often a fairly large amount of data. Right? A lot of this was thanks to the digitization of a society where so much human activity is now in the digital realm. We spend so much time on our computers, on websites, on mobile apps, and activities on digital devices creates data. And thanks to the rise of inexpensive cameras built into our cell phones, accelerometers, all sorts of sensors in the Internet of Things, we also just have been collecting more and more data. So over the last 20 years, for a lot of applications, we just accumulated a lot more data, more than traditional learning algorithms were able to effectively take advantage of. And with neural networks, it turns out that if you train a small neural net, then its performance maybe looks like that. If you train a somewhat larger neural net, let's call this a medium-sized neural net, its performance often even a little bit better. And if you train a very large neural net, then its performance often just keeps getting better and better. So a couple observations. One is, if you want to hit this very high level of performance, then you need two things. First, often you need to be able to train a big enough neural network in order to take advantage of a huge amount of data. And second, you need to be out here on the x-axis. You do need a lot of data. So we often say that scale has been driving deep learning progress, and by scale, I mean both the size of the neural network, meaning just a neural network with a lot of hidden units, a lot of parameters, a lot of connections, as well as scale of the data. In fact, today, one of the most reliable ways to get better performance in a neural network is often to either train a bigger network or throw more data at it. And that only works up to a point, because eventually you run out of data, or eventually the neural network is so big that it takes too long to train. But just improving scale has actually taken us a long way in the world of deep learning. In order to make this diagram a bit more technically precise, let me just add a few more things. I wrote amount of data on the x-axis. Technically, this is amount of labeled data, where by labeled data, I mean training examples, we have both the input x and the label y. Oh, and to introduce a little bit of notation that we'll use later, in this course, we're going to use lowercase alphabet m to denote the size of our training set. So the number of training examples is lowercase m, so that's the horizontal axis. A couple other details to this figure. In this regime of small training sets, the relative ordering of the algorithms is actually not very well defined. So if you don't have a lot of training data, it's often up to your skill at hand engineering features that determines performance. So it's quite possible that if someone training an SVM is more motivated to hand engineer features than someone training an even large neural net, maybe in this small training set regime, the SVM could do better. So, in this region to the left of the figure, the relative ordering between the algorithms is not that well defined. And performance depends much more on your skill at handling features and other little details of the algorithms. And it's only in this big data regime, very large training sets, very large M regime on the right, that we more consistently see large neural nets dominating the other approaches. And so if any of your friends ask you, why are neural nets taking off, I would encourage you to draw this picture for them as well. So I would say that in the early days, in the modern rise of deep learning, it was scale of data and scale of computation. Just our ability to train very large neural networks, either on a CPU or a GPU, that enabled us to make a lot of progress. But increasingly, especially in the last several years, we've been seeing tremendous algorithmic innovation as well. So I also don't want to understate that. Interestingly, many of the algorithmic innovations have been about trying to make neural networks run much faster. So, as a concrete example, one of the huge breakthroughs in neural networks has been switching from a sigmoid function, which looks like this, to a ReLU function, which we talked about briefly in an earlier video, that looks like this. If you don't understand the details of what I'm about to say, don't worry about it. But it turns out that one of the problems of using sigmoid functions in machine learning is that there are these regions here where the slope of the function, where the gradient is nearly zero, and so learning becomes really slow. Because when you implement gradient descent and the gradient is zero, the parameters just change very slowly, and so learning is very slow. Whereas by changing the what's called the active, which looks like this, to a ReLU function, which we talked about briefly in an earlier video, that looks like this. If you don't understand the details of what I'm about to say, don't worry about it. But it turns out that one of the problems of using sigmoid functions in machine learning is that there are these regions here where the slope of the function, where the gradient is nearly zero, and so learning becomes really slow. Because when you implement gradient descent and the gradient is zero, the parameters just change very slowly, and so learning is very slow. Whereas by changing what's called the activation function of a neural network to use this function called the ReLU function, or the rectified linear unit, ReLU, the use of input, right? And so the gradient is much less likely to gradually shrink to zero. And the gradient here, the slope of this line is zero on the left, but it turns out that just by switching to the sigmoid function, to the ReLU function, has 1 for all machine learning, is that there are these regions here where the slope of the function, where the gradient is nearly zero, and so learning becomes really slow. Because when you implement gradient descent and the gradient is zero, the parameters just change very slowly, and so learning is very slow. Whereas by changing what's called the activation function of a neural network to use this function called the ReLU function, or the rectified linear unit, ReLU, the gradient is equal to 1 for all positive values of input, right? And so the gradient is much less likely to gradually shrink to zero. And the gradient here, the slope of this line is zero on the left, but it turns out that just by switching to the sigmoid function, to the ReLU function, has made an algorithm called gradient descent work much faster. And so this is an example of maybe a relatively simple algorithmic innovation, but ultimately the impact of this algorithmic innovation was it really helped computation. So there have actually been quite a lot of examples like this of where we change the algorithm because it allows our code to run much faster, and this allows us to train bigger neural networks. Innovation was it really helped computation. So there have actually been quite a lot of examples like this of where we change the algorithm because it allows our code to run much faster, and this allows us to train bigger neural networks, or to do so in a reasonable amount of time, even when we have a large network or a lot of data. So in a reasonable amount of time, even when we have a large network or a lot of data. The other reason that fast computation is important is that it turns out the process of training neural network is very iterative. Often you have an idea for a neural network architecture, and so you implement your idea in code. Implementing your idea then lets you run an experiment which tells you how well your neural network does, and then by looking at it, you go back to change the details of your neural network, and then you go around this circle over and over. And when your neural network takes a long time to train, it just takes a long time to go around this cycle. And there's a huge difference in your productivity building effective neural networks when you can have an idea and try it and see if it worked in 10 minutes, or maybe at most a day, versus if you have to train your neural network for a month, which sometimes does happen. Because when you get a result back, in 10 minutes or maybe in a day, you could just try a lot more ideas and be much more likely to discover a neural network that works well for your application. And so faster computation has really helped in terms of speeding up the rate at which you can get an experimental result back. And this has really helped both practitioners of neural networks as well as researchers working in deep learning iterate much faster and improve your ideas much faster. And so all this has also been a huge boon to the entire deep learning research community, which has been incredible at just inventing new algorithms and making non-stop progress on that front. So these are some of the forces powering the rise of deep learning. But the good news is that these forces are still working powerfully to make deep learning even better. Take data. Society is still throwing off more and more digital data, Or take computation, with the rise of specialized hardware like GPUs and faster networking, many types of hardware. I'm actually quite confident that our ability to build very large neural networks from a sheer computation point of view will keep on getting better. And take algorithms, well, the whole deep learning research community is still continues to be phenomenal at innovating on the algorithms front. So because of this, I think that we can be optimistic. I'm certainly optimistic that deep learning will keep on getting better for many years to come. So with that, let's go on to the last video of this section, where we'll talk a little bit more about what you learned from this course. So you're just about to reach the end of the first week of material on the first course into specialization. Let me give a quick sense of what you learned in the next few weeks as well. As I said in the first video, this specialization comprises 5 courses, and right now we're in the first of these 5 courses, which teach you the most important foundations, really the most important building blocks of deep learning. So by the end of this first course, you know how to build and get to work a deep neural network. So here are the details of what is in this first course. This course has 4 weeks of material, and you're just coming up to the end of the first week where you saw an introduction to deep learning. At the end of each week, there'll also be 10 multiple choice questions that you can use to double check your understanding of the material. So when you're done watching this video, I hope you go on to take a look at those questions. In the second week, you then learn about the basics of neural network programming. You learn the structure of what are called the forward propagation and the back propagation steps of the algorithm, and how to implement neural networks efficiently. Starting from the second week, you also get to do a programming exercise that lets you practice the material you've just learned, implement the algorithms yourself, and see it work for yourself. I find it really satisfying when I learn about an algorithm and I get to code it up and I see it work, for myself. So I hope you enjoy that too. Having learned the framework for neural network programming, in the third week, you code up a single hidden layer neural network. All right. So you learn about all the key concepts needed to implement and get to work a neural network. And then finally in week 4, you build a deep neural network, a neural network with many layers, and see it work for yourself. So with that, congratulations on finishing the videos up to this one. I hope that you now have a good high-level sense of what's happening in deep learning. And perhaps some of you are also starting to have some ideas of where you might want to apply deep learning yourself. So I hope that after this video, you go on to take a look at the 10 multiple choice questions that follow this video on the course website, and just the 10 multiple choice questions to check your understanding. And don't worry if you don't get all the answers right the first time, you can try again and again until you get them all right. I found them useful to make sure that I'm understanding all the concepts. I hope they'll help you that way too. So with that, congrats again for getting up to here, and I look forward to seeing you in the week 2 videos. I hope you enjoyed this course, and to help you complete it, I want to make sure that there are a few course resources that you know about. First, I hope you enjoyed this course, and to help you complete it, I want to make sure that there are a few course resources that you know about. First, if you have any questions or you want to discuss anything with the classmates or the teaching staff, including me, or if you want to file a bug report, the best place to do that is the discussion forum. The teaching staff and I will be monitoring that regularly, and this is also a good place for you to get answers to your questions from your classmates, or, if you wish, try to answer your classmates' questions. To get to the discussion forum from this course homepage, if you look at this menu bar on the left, yours might look a bit different than mine, but there'll be this discussion forum tab, which if you click on, gets you to the discussion forum. The best way to ask questions is on the discussion forum, but if for some reason you need to contact us directly or let us know about some problem, feel free also to email us at this email address. I promise we will read every email and we'll try to address commonly occurring issues, although depending on the email volume, I can't guarantee that we'll be able to reply promptly to every email, but we will read every email that you send. Next, I know that there are a lot of companies that wish to course, and to help you complete it, I want to make sure, but we will read every email that you send. Next, I know that we'll be able to reply promptly to every email, but we will read every email that you send. Next, I know that there are a lot of companies that wish to train maybe large numbers of employees with deep learning. If you're responsible for employee training in your company and would like to train 100 or more employees with deep learning expertise, please feel free to get in touch at this email and we'll see if we can help you. We're just in the early phases of developing the university academic program, but if you're a university instructor or a university administrator interested in offering a deep learning course at your university, please feel free to contact us at this email address. So I hope this gives you more resources to complete the class. Maybe I'll see some of you in the discussion forums, and best of luck. As part of this course by deep learning, AI, I hope to not just teach you the technical ideas in deep learning, but also introduce you to some of the people, some of the heroes in deep learning, the people that invented so many of these ideas that you learn about in this course or in this specialization. In these videos, I hope to also ask these leaders of deep learning to give you career advice for how you can break into deep learning, for how you can do research or find a job in deep learning. As the first of this interview series, I'm delighted to have to present to you an interview with Geoffrey Hinton. Welcome, Jeff, and thank you for doing this interview with deeplearning.ai.
Thank you for inviting me.
I think that at this point, you more than anyone else on this planet has invented so many of the ideas behind deep learning. And a lot of people have been calling you the godfather of deep learning, although it wasn't until we're just chatting a few minutes ago that I realized you think I'm the first one to call you that, which I'm quite happy to have done. But what I want to ask is, many people know you as a legend. I want to ask about your personal story behind the legend. So how did you get involved in, going way back, how did you get involved in AI and machine learning and neural networks?
So when I was at high school, I had a classmate who was always better than me at everything. He was a brilliant mathematician. And he came into school one day and said, "Did you know the brain uses holograms?" And I guess that was about 1966. And I said, "So what's a hologram?" And he explained that in a hologram, you can chop off half of it and you still get the whole picture. And that memories in the brain might be distributed over the whole brain. And so I guess he'd read about Lash's experiments where you chop out bits of a rat's brain and discover it's very hard to find one bit where it stores one particular memory. So that's what first got me interested in how does the brain store memories. And it was about 1966. And I said, sort of, what's a hologram? And he explained that in a hologram, you can chop off half of it and you still get the whole picture. And that memories in the brain might be distributed over the whole brain. And so I guess he'd read about Lashley's experiments where you chop out bits of a rat's brain and discover it's very hard to find one bit where it stores one particular memory. So that's what first got me interested in how does the brain store memories. And then when I went to university, I started off studying physiology and physics. I think when I was at Cambridge, I was the only undergraduate doing physiology and physics. And then I gave up on that and tried to do philosophy because I thought that might give me more insight. But that seemed to me actually lacking in ways of distinguishing when they said something false. And so then I switched to psychology. And in psychology, they had very, very simple theories. And it seemed to me it was sort of hopelessly inadequate for explaining what the brain was doing. So then I took some time off and became a carpenter. And then I decided I'd try AI. And I went off to Edinburgh to study AI with Longa Higgins. And he had done very nice work on neural networks. And he'd just given up on neural networks and been very impressed by Winograd's thesis. So when I arrived, he thought I was kind of doing this old-fashioned stuff and I ought to start on symbolic AI. And we had a lot of fights about that, but I just kept on doing what I believed in.
And then what?
I eventually got a PhD in AI, and then I couldn't get a job in Britain. But I saw this very nice advertisement for Sloan Fellowships in California. And I managed to get one of those. And I went to California, and everything was different there. So in Britain, neural nets was regarded as kind of silly. And in California, Don Norman and David Rumelhart were very open to ideas about neural nets. It was the first time I'd been somewhere where thinking about how the brain works and thinking about how that might relate to psychology was seen as a very positive thing. And it was a lot of fun there. In particular, collaborating with David Rumelhart was great.
I see, right. So this is when you were at UCSD and you and Rumelhart around, what, 1982, wound up writing, the seminal backdrop paper, right? So
actually, it was more complicated than that.
What happened?
So I think, around early 1982, David Rumelhart and me and Ron Williams, between us, developed the backdrop algorithm. It was mainly David Rumelhart's idea. We discovered later that many other people had invented it. David Parker had invented it, probably after us, but before we published. Paul Werbos had published it already quite a few years earlier, but nobody paid much attention. And there were other people who developed very similar algorithms. It's not clear what's meant by backprop, but using the chain rule to get derivatives was not a novel idea.
Why do you think it was your paper that helped so much the community latch onto backprop? It feels like your paper marked an inflection in the acceptance of this algorithm, whoever accepted it.
So we managed to get a paper into but nobody had paid it much attention. And there were other people who developed very similar algorithms. It's not clear what's meant by backprop, but using the chain rule to get derivatives was not a novel idea.
Why do you think it was your paper that helped so much the community latch on to backprop? It feels like your paper marked an inflection in the acceptance of this algorithm, whoever accepted it.
So we managed to get a paper into Nature in 1986, and I did quite a lot of political work to get the paper accepted. I figured out that one of the referees was probably going to be Stuart Sutherland, who was a well-known psychologist in Britain. And I went and talked to him for a long time and explained to him exactly what was going on. And he was very impressed by the fact that we showed that backprop could learn representations for words, and you could look at those representations, which were little vectors, and you could understand the meaning of the individual features. So we actually trained it on little triples of words about family trees, like Mary has mother Victoria, and you'd give it the first two words and it would have to predict the last word. And after you trained it, you could see all sorts of features in the representations of the individual words, like the nationality of the person and their what generation they were, which branch of the family tree they were in, and so on. That was what made Stuart Sutherland really impressed with it, and I think that was why the paper got accepted.
Very early word embeddings, and you're already seeing features, learned features of semantic meanings emerge from the training algorithm.
Yes, so from a psychologist's point of view, what was interesting was it unified two completely different strands of ideas about what knowledge was like. So there was the old psychologist's view that a concept is just a big bundle of features, and there's lots of evidence for that. And then there was the AI view of the time, which is a far more structuralist view, which was that a concept is how it relates to other concepts. And to capture a concept, you'd have to do something like a graph structure, or maybe a semantic net. And what this backpropagation example showed was you could give it the information that would go into a graph structure, or in this case, a family tree, and it could convert that information into features in such a way that it could then use the features to derive new consistent information, i.e. generalize. But the crucial thing was this to and fro between the graphical representation, or the tree structured representation of the family tree, and a representation of the people as big feature vectors. And the fact that you could, from the graph-like representation, you could get to the feature vector.